2.5 isn't a really long assignment. One thing that I probably cannot stress enough is we're going to look at symmetry. And if it's symmetric in terms of the y-axis. When it is, what you're going to notice is the x values are the same but with opposite signs. When it is symmetric to the x-axis, your y values have opposite signs. They're same number just with opposite signs. When you, if it's symmetric in respect to the origin, get the right word here, both of them are opposite, the x and the y. So they're the same numbers just with opposite signs. And that's going to be the theme of every single thing we do today in this 2.5. And it's going to seem really redundant. It's just applying it in different little ways. Okay, so if we look at these graphs, this will just be kind of the foundation of it all. I like to put little hash marks in here so I can make them ordered pairs rather than just calling x's and y's. So I'm going to put 3 of them and then 2. So this is a graph that is in respect to your y-axis. And I like to just write it above. It's stated below, but I like to write it above bigger so it looks like a better label. So what happens here is this ordered pair would be like saying 3, 2. You'd move over 3 and up 2. This ordered pair, you'd have to go to the left, but still up 2. So the numbers are the same, but your x values are opposite signs. So the pattern I'm going to go over and over and over with this 2.5 stuff that will help you a lot is just that if it's in respect to the y-axis, when you're talking about your coordinate, the opposite letter has opposite signs. Right? I'll say it again as we do some more. So here, this one is a graph or an example of a graph that is in respect to the x-axis. It's symmetric in respect to the x-axis. I always leave that word out. Symmetric. If you were to fold it on the x-axis, these 2 points would line up. So again, if I went over 3 and up 2 in this case, this point up here would be 3, 2. We'd still go over 3, but my y part would be a negative 2. So if it's the x-axis, the opposite letter is y, when you're talking about ordered pairs, right? The y's have opposite signs. And then what you're going to notice about the origin is it's usually like a little curvy line that kind of looks like a wave of sorts. If this was, I put 2 hash marks and then 4 to get there. If this ordered pair was 2, 4, if you went over 2 and up 4 to get to that point, then you would have to go to the left 2 and down 4 to get to that point. So this one is an example where they were both positive and we changed both signs to negative. So I feel like what we're about to do now is just going to be incredibly redundant, but it's just different ways it's being applied. So if you can remember that, no matter what you do with symmetric in respect to the x or y axis or origin type questions, you're going to be good. So we're going to do that again, but they're not telling us underneath what it is. We have to label it ourselves. Do you think this one's going to be in respect to the x-axis, the y-axis, or the origin?
The origin.
The origin, and that one's pretty easy, wouldn't you say, because it's kind of wavy, right? We wouldn't even have to compare points, but like on your graph, you may want to compare points, like pick a couple points to compare, so that's why I put 2 points there. So like, let's just say if this was, I know they're counting by halves on your graph, but I'm always just go by a scale of 1. That would be like saying 3, 2. Then you'd have to go to the left 3 and down 2, right? So they have opposite signs. Both x's and y's do. What do you think about this one? If you could fold this graph,
Y.
it's going to be the y-axis, right? And so again, basically what we're learning is, obviously it's easy to think if I folded it, that did that, but if you see the ordered pairs, this would be like -2, 0, and this would be like 2, 0. The x values have opposite signs. Kind of difficult to have opposite signs with 0. This one I would maybe like put right here. I would probably call that 2 though, just to make it a little bit better. Do you think that is being folded on the x or the y-axis?
X.
The x-axis. Visually, it's pretty easy to see those things. What's happening with the ordered pair is you're still going over to 2, but you would go down to -1 for that one. You'd go over to 2, and you would go up. So the y parts, we're changing signs. And that helps us when we go do it algebraically. There's a test for symmetry when we turn the page that we're going to be doing. And actually, I guess we have to plot some points first. I was like already ahead of myself. But we will be doing some things algebraically, and you'll see why I'm like really going over the changing of the sign of the x or the y part of the coordinate. Example here says consider this point 7, -4. We want to plot an image of the point with respect to the y-axis. So what I would do, you have one like this like in your homework. If it's in respect to the y-axis, the x part changes signs. So that means if it was a 7, the x needs to be a -7. So that would be at -7, -4. So you don't have to go plot that given point. Can't remember if they give it to you or not. I kind of feel like they don't, but 1, 2, 3, 4, 5, 6, 7, down 4. 1, 2, 3, 4 is right here. That's that original point that they say. If I wanted to say in respect to the y-axis, you know it'd have to be over here because you're folding it, right? So you'd have to go to the left 7. 1, 2, 3, 4, 5, 6, 7, down 4. So it's just easier to kind of remember that instead of just figuring it out by looking at a graph. Like if you were looking at the point, what is the ordered pair of that point? They may have it plotted for you. What would it be? Maybe it's 7, 4, -4. And you would know if I was plotting a point in respect to the y-axis, it'd have to change the x's sign to get that ordered pair. How about if I were plotting an image with respect to the x-axis? Which part of the coordinate changes signs? The y. So 7 stays the same, and we now have a +4. So we'd go over 7. 1, 2, 3, 4, 5, 6, 7, up 4. 1, 2, 3, 4. And I'm just plotting that original one there. So this would be 7, 4. Kind of boxing it out so you don't get confused on the original one. Why? I just plot it just for visual reference. And if I'm plotting an image in respect to the origin, what am I doing with the signs?
Flipping both the signs.
Both of them. -7 and +4. So again, this is kind of like 1, 2, 3, 4, 5, 6, 7. Down 4 is still here. But if we were changing both signs, we'd go over 7. 1, 2, 3, 4, 5, 6, 7, up 4. 1, 2, 3, 4. So it's in total opposite of both your x and your y. So do you feel like you're getting what's happening with ordered pairs? If it's in respect to it, okay. Because it really helps with everything else. I feel like I say it a lot. But, so when we do tests for symmetry, algebraically, with respect to either the x or the y-axis, up here it says, if we're testing the y-axis, which is the one I usually do first as well, we're going to replace x with a negative. You know, we're replacing the opposite letter with a negative in front of it. And then we're going to go simplify the negatives to see if it changes the equation or not. If it leaves it unchanged, if it ends up matching after we simplify those negatives back out of it, then it is in respect to it. Let me show you what I mean. So I always do the y-axis one first. I think it's because what I'm doing is putting a negative in front of my x variable, the opposite letter, right? And squaring it. And then I just go simplify. A negative x times a negative x is still a positive x squared. So this matches that exactly. So we could say that this one would be in respect to the y-axis. Without even having to graph it, we could just know algebraically that is the test of symmetry that you can do. I'm going to show you, if you do it and it works, you don't have to go try the other one, but just for lecture purposes, I'm going to go show you, what if you would have tried the x-axis? What would it look like? What does it mean? It alters the equation is what that's going to do, but let's go do it. So I'm going to put a negative in front of which letter this time?
Y.
The y. And then, again, when I say simplify the variable part, this is where, like, I'm trying to make it match this, so I know I don't want a negative y, so I divide everything by a negative 1. And do you see how the signs all change to the opposite of what we need over here? So we would say that alters the equation by changing that variable y to a negative. It alters the equation, so it could not be in respect to the x-axis. So sometimes you're going to check it, and that it's going to happen that way. You know, the first one isn't going to work out always. So looking at B, remember what absolute value is, right? It's like the distance from 0 and the number line. And if you plug a number in there, whether it's positive or negative, you're always moving the same amount, right? It always is a positive number. So if I'm checking this one to see if it is symmetric in respect to the y-axis, remember you're putting a negative sign in front of the x variable. So this time x is on the left.
Can you push the paper up?
Yes, I can. Sorry. I didn't even look over there. Sometimes I'm good at that, sometimes I'm not. So putting a negative in front of that x value, so what we would do, again, we want to see if I simplify and make that a positive x, does this side stay the same? So we would divide everything by a negative 1, so x would equal a negative would be out in front of that absolute value bracket, and this would be a positive 2. So all of that stuff changed, didn't it? So this alters the equation, so we know it's not that. So it's not the y-axis. We need to see if it's in respect to the x-axis. And by the way, just because one doesn't work doesn't mean it's always the other. It could be neither. In our notes, it's one or the other, but it could be neither. So always check both of them if the first one doesn't work. So x equals, if you're putting a negative in there because of those absolute value, it's inside that absolute value bracket. That's also kind of why I reviewed that. If I were simplifying the absolute value of negative y, is that the same as the absolute value of positive y?
Yes.
Yeah, so technically, even though it looks a little bit different, it's not going to alter what happens in the end, right? So we would say it's in respect to the x-axis. I didn't write it above, did I? I should. I'm going to do that. So again, I'm just going to explain that one more time because I know sometimes absolute value, we don't hit it very much. But if I take the absolute value of negative y and the absolute value of y, I get y. So if you were to go like simplify them both, they still are both going to look like y minus 2, right? So that's why with the absolute value that it is in respect to the x-axis. Do you guys know what the graph of an absolute value equation usually looks like?
Is it a V?
Yeah, it's a V. So think about that. That's where your like vertex would be, you know. Okay. And then just another way to start talking. Oh, this one's the origin. What do you think we're going to do to the variables with x and y? We're going to put negatives in front of both of them this time, and then see if when you simplify it, if it changed it or not. And so this one is either going to be in respect to the origin or not. It's not compared with any other thing. Okay, it's just alone. So negative x times a negative y equals 4. Well, we know if a negative times a negative makes a positive, it's still just xy equals 4 in the end, right? So it ended up matching the given one, so we would say this is symmetric in respect to the origin. Yes. And then we do the same thing on part B to try one more example of determining if it's in respect, if it has symmetry in respect to the origin. We change the y and the x, so negative y equals a negative x. Just put it in a parentheses, just because, I guess, like draw attention to the fact that there's a negative in front of it. But when we start simplifying this one, we know negative x to the third power would still be a negative x. And then what would we need to do?
Divide the y, the negative out of it.
Right, divide the negative out of the y, because what we want to do is say, well, the given problem has a positive y, so let's see what happens when we make y positive. So y equals a positive x to the third, but a negative 1. So there is a change. It's just one change, but it is a change. So we would say not in respect to the origin. Or just say no. But we don't go try anything else. We don't see if it's in respect to anything else. You just, because it doesn't label anything else with it. It's always just alone. The x and y's, they will label together. They will say, is that in respect to the x-axis or the y-axis? The origin is just standalone. It either is or it isn't. So a little thing that we talk about but we just really don't do a lot with, they label some of these called even and odd functions. And so what that means is if it's an even function, and just highlight it, it means when I change the sign for x, that's why they have a negative in there, the y stays the same. It doesn't change the sign of y. If it did, there'd be like a negative in front of your f. So if we change the sign of x, the y stays the same. So if it's an even function, we say that's in respect to the y-axis. Only thing that changed was you altered the x, right? The x changed. Keep going back to that. The opposite axis. The y stayed the same. So in respect to the y-axis. An odd function is said to be in respect to the origin. What this means is if you change the x, the y changes. I feel like sometimes function notation can be confusing. So it's hard for me to explain it unless we've had a lesson on function notation. But in here, that's with the variable x. Your solution is your y, what they call it f of x. And so if they're changing the sign of it, it would be out in front. So this is like you're changing the x and the y. If you like to see it like this, you know, like just if you were comparing x and y, that can kind of help you. That's basically what's happening. So there's not one for x-axis with even and odd functions. So what you do is, if we're labeling it an even function, let's go to that. Let's go to part B first. If we're labeling it an even function, what this means is if I change the x to a negative if the equation remains unchanged. When you simplify, it could, right? Because doesn't negative x and positive x absolute value equal the same thing, right? This is like technically unchanged. It's not changing the y part. It's not changing the function at all. We call this an even function. So you change the x, but the equation is unchanged. That might help you kind of understand that instead of just x's and y's, which is what we're used to calling y. But if you change the x, like this one, it changes the equation. So this one is an odd function. So I guess if you have a memory device, if you change the x and the y changes, they both change. That's odd. I don't know. Find a memory device that works. So when you change your x to a negative, the y part changes, or the solution, the equation, that's the word I was looking for, the equation changes, just to the opposite sign. But it really only works if you have one term over there for the most part. I can't like say a blanket statement of that because there's probably something in there that is an exception to the rule. You can also have neither, and a neither would look kind of like this. You're still changing the x values to negatives. And then if you notice, this one stays a positive, and this one becomes a negative 2x. So like one changed, one didn't, so we would call that neither. It does change the equation overall, but it doesn't change both of the terms that have x. So now that we know if a function is odd and even, how does that even help us? It helps a lot. It's really just like if you look at these equations, like this is an even function. Notice if you folded this, you could fold it on the y-axis and all these points, these lines would meet up. So just visually, that would be referred to like an odd function. Also in respect to the y-axis, just another way of saying it with another name. Okay, this one would be the origin. If we like compared these two endpoints, those are the easiest ones for me to do. That would be considered an odd function. You know that they're, opposite signs for both your x and y. Ordered pairs would be the best way to do that. That's in respect to the origin. What it does help us with is like this. Sometimes graphs can be shifted. Do you remember translations? So maybe it's been moved. That's how it helps us. No, if it's an even or an odd function, there's something else happening making you shift that function. And so this one would be one like, this would be the vertex. I'd have to fold it on the x-axis, not the y-axis. It wouldn't be at the y-axis. I'd have to fold it, and the x part is what's telling you like it's symmetry, right? Axis of symmetry. So basically it tells us if it's been transitioned or not. So we're going to talk about that. Got just one more page and we'll be done. I know it's a lot. And it's a lot of repetition, really. So do you guys remember the word parent function now? Okay, kind of really digging back to some old stuff. So going off of what we're talking about, translations of graphs, like this is a parent function. You can hardly see the actual function itself, but that's f of x equals 2 to the x power. So if you change that function by like adding or subtracting a number from 2 to the x power, that means you're going to be moving it up or down. So in this case, this equation right here, to make it bigger, was f of x equals, I'm going to write it below, 2x minus 3. So since it's a minus 3, you're going to go down 3. So if you were comparing this point from the parent function and you just moved down 3 places, that's a point you could compare from it. And then from there, the graph kind of does its thing. If it's moving to the right or to the left, generally you're going to have it adding or subtracting from the variable itself. Like this was subtracting from this term, but this is the parent function, which was the same as what we saw before, 2 to the x power. This function says g of x, they didn't use f of x this time, I don't know why, but g of x equals 2, and they're subtracting from the variable. I like to put it in a parentheses because it just helps me remember that it's being subtracted from the variable itself. If that happens, you're moving right or left, and you're moving the opposite direction of what you would think. Because it's in there with the x, you know, if you were like to get it by itself, it'd be the opposite sign. But we're going to move to the right 3. So let's say, again, we're like comparing this point, like to compare the points that cross the y-axis when I can. Those are the best. And if you move over 1, 2, 3 points, you would be over there. So if you hated translations of graphs, don't stress out too much because we really don't spend a whole lot of time, but if you can pick up on just those small things, for sure. If you're adding or subtracting from the whole term itself, that's moving up or down. If you're adding or subtracting from x, from the variable, then you're moving right or left, and make sure you're going opposite of what you would think. -3 makes me think left, but you would go right. So if we're practicing that and applying it, if I say g of x minus 2, this is the parent function graph. I don't really even know the equation. It's probably an absolute value something. Okay? If I said that minus 2, am I going up or down, right or left?
Up or down?
Up or down, because I'm not really like, this would be like the function, whatever that is, and I'm subtracting 2 from the entire function. So I'm going down 2 and just kind of making a V. Doesn't have to be perfect. And this one, it's subtracting from the variable. So you have your g function, but in the variable part,
Going up, or you're gonna go right or left?
you're going to go right or left. Yeah, very good. So it's kind of a hard one. But since it's +3, we're going right. I mean, there's a 50-50. You can get it right or wrong, 50-50, right?
Just told us.
If that was +3, you would have gone to the left, correct?
Yeah.
If this was +2, you would have moved up.
Yeah.
Okay, just kind of going back over that. So again, reflections of graphs. We're going back to reflections, but really this probably should not say reflections. Translations of graphs, they do closely resemble symmetry, but we're not just changing x and y's signs or both, right? You're like moving to a whole entire new point is all the translation should be. So really this should not say reflections, it should say translations. But so one more time about reflections, which again is changing your x or y's or both. If you were looking at this, is this symmetric to the x or the y axis?
X.
X. How do we know that? If you fold it at the x-axis, they're going to change. Is this symmetric to the x or the y-axis?
The Y.
The y. So are we getting this? This is symmetric to the x-axis, and this is the y-axis. Again, just think if you were folding that paper, if you fold it on the y-axis, then it's symmetric to the y-axis. Okay? And so we get to just practice that. I don't really make you do this, but we get to practice that, and it's that function notation that's very weird, that we don't spend a lot of time on with you guys. But basically, your x and then your y changes. Let's look at it like that. So if the y changes, what axis do you think is in respect to?
X.
Yeah, this would be in respect to your x-axis. So that would be like here. So this one is like you're changing, it's backwards. compared to what you're used to, it's like, maybe this would be your solution, but you changed the x. And I'm saying that because it's inside the parentheses with x. So if the x changes, then that's in respect to the y-axis. So this would be if you want to label your g of x, and then this one would be your h of x.